welcome everybody. I'm Kimish Patel. This is my colleague Chen. We both of us work at AI at Meta, and we are part of a PyTorch Edge team. We are excited here. We are delighted here to be sharing our vision for accelerating AI models via partner integration. Right. So, before I tell you how we're gonna do this, I must first answer like why partner integration matters, right? So for that, I want us to take a look at what the current landscape of on-device AI is like. I admit that this picture is somewhat PyTorch-centric, but if you see from a trained, generally what happens on the journey of deploying a PyTorch model on a device is that you have a trained PyTorch model that often leaves a PyTorch ecosystem. You go into another converter that converts that into another IR that is represented by representation of the converter. And from there on, or sometimes often from the PyTorch model, original model itself, you go to vendor-specific toolchains that eventually lower the converted IR to the toolchain-specific IR. This is the IR that the toolchains understand, and they can translate and do the device-specific transformations on those. At this point is when you actually get the artifacts that you eventually deploy on device. And the number of devices you see here have a high level of diversity. So what happens as a result of this is that this landscape where you actually deploy these models is characterized by diversity of hardware, specifically on the Android ecosystem. You have many different OEMs and chipsets and manufacturers and things like that. Furthermore, if you go beyond the phones itself, you have diversity of OS or the lack of one. Like in some of the embedded environments, there's absolutely no OS, or if they have one, they are like some real-time operating system which are proprietary for specific vendors. Beyond that, from the hardware diversity itself, there are a lot of different chipsets and proprietary IPs that are used by these OEMs that come from a lot of different parts of the world. And each of these different IPs and hardware have their own proprietary tool chains and compilers and things like that, right? So this is why deploying on device becomes harder. Now, because of this diversity, what happens in most of the current production workflow that take a PyTorch model for a deployment on device is that you have multiple conversion scripts that take the PyTorch model, convert to another IR, that take that converted IR and go to the lowering process, which has its own set of scripts, and eventually get the deployed model. And this results in loss of information. Why? Because when you go from one IR to another IR, it's like going from one domain to the another domain, which are speaking completely different languages, right? And each of these language, they are different enough that they have a loss in translation. So by the time you actually deploy the original PyTorch model on device, it is no longer a PyTorch model. So you don't know if you wanted to understand what part of that model comes from what your original PyTorch code was. You have lost that information, right? Now, you could say that, okay, fine, I lost a lot of information, but I actually did get performance, right? I was able to accelerate my model on a specific hardware, and that was great. Maybe I also got reach of, and by reach, what I mean is that you are able to deploy some of these models on some devices. And it's only some because the nature of these tool chains is such that the lowering process is all or nothing. So you either lower the entire model or not lower the entire model. So it restricts the number of models and number of devices that you can actually target. So, okay, you got reach, but not a lot. And when I say you, this is actually the end user, right, who is the ML engineers or deployment engineers. But what you lose because of these conversions and going from one domain to another domain is one, portability, which means that your production code now needs to be aware of what device or platform you are running your model on. This is because you have to now use it, because you left PyTorch ecosystem and to the entirely other ecosystem, you need to be aware of what are the model loading and running runtime and model loading APIs, or even the profiling APIs and things like that. You lose productivity. Why? Because now the deployment engineers have to deal with 10 different tool chains, which are specific to each each different device or platform that you want to deploy the same PyTorch model on. And each of those toolchains may have their own set of lowering errors that you now have to take back to the original PyTorch model, maybe modify your code in a way that it still makes it lowerable. So this entire process of conversion process, finding lowering errors, fixing those, and round trip time is long enough that it becomes quite unproductive for even to lower a single model. And we have seen this actually in a lot of use cases that we have had. And lastly, you also lose coverage. Now, by coverage, I mean you not only you lose coverage across the number of devices you can target, but you also lose coverage in terms of what kind of models you can target. Remember I said that the lowering process is all or nothing, right? So if you have a model which is only part of the model can be run on acceleration or some device-specific hardware, now you can't just say that, okay, I want to run only that piece over there, right? So this is what ends up happening, that you gain some performance, maybe some reach, but you internally are losing a lot of things. So you would say like, well, wow, thank you for all the doom and gloom. But, so yes, it's not great, but what ideally we would like is a silver bullet that can target all of the pain points that we have had. And if I had to think of one, that would consist of sort of federation where vendors, OEM partners come together and become part of the PyTorch and executor ecosystem. And that is what I want to sell today, right? That's what we are here for. So what it can achieve. So this is exactly the vision that we are talking about, right? Going earlier from the fragmented ecosystem where each vendors have their own tool chains, or lowering scripts and things like that. If you want to advocate for something where we are able to provide a set of integration entry points into which different partners would integrate into and become part of PyTorch and executor ecosystem. And by doing that, what we now are able to get is the same performance that we were getting before. We are getting wider reach because now, by working with our partners, we are able to target larger segment, larger fraction of the spectrum that exists in terms of all the different OEMs, vendors, chipsets that exist. So we get reach, we get portability because now the same executor model can be deployed on any of these devices without users having to change their APIs. Why? Because the partner integration enables, what it enables is that the deployment code does not have to be aware of the fact that, oh, this model is accelerated for this device on this specific Android phone or this specific iPhone. It looks the same from the user runtime API perspective. From productivity, what you get is that because you are working on a standard set of operators, and the IR on using which the lowering works, on which the partner integration points work, it makes it easy for you to reason about if the lowering errors happen, where do they come from in your original PyTorch code, which makes the round trip time, if needed, much more easier. Furthermore, you also get functional and performance debugging, right? So what that means is that because of this native integration in the ecosystem, now if the part of a model is running slow, you can say where that part of the model comes from in the original PyTorch code. And maybe you can work with figuring out, okay, on this specific device, actually that one runs slow, so maybe I need to change my model for deploying on this set of hardware. So you become more productive in optimizing your models. And you get coverage because when the only part of your models are accelerated, but rest is not, the composable nature of these entry points enables you to lower only what can be accelerated on the hardware. What cannot be can be handled by the rest of the stack, be it another special software stack or native executor runtime itself. Right? All right. So, and for vendors, what that means is that, so what I just talked about was like from the user perspective, the ML engineers or deployment engineers, what's the advantage? From vendor perspective, what this means is that they are only now have to worry about the entry points that are provided by the stack without having to worry about what the rest of the stack does. So it gives you a self-contained API, and that provides you an isolation, and which works in relation with the composable nature of this, right? So what you cannot handle, you can let the rest of the stack handle, and you only worry about optimizing what you know how to do the best. All right, so when we have achieved that vision, what that enables us to do is that for ML engineers, now they're able to deploy their PyTorch models on more set of hardwares and more set of devices, be it phones or embedded devices, whatever have you. It increases their reach without sacrificing any of this performance, productivity, or portability. And from partner perspective, what that means is that you are now able to unlock more PyTorch models on your platforms, which in turn incentivizes more investment, right? So it forms a positive feedback loop where users are able to deploy more of their models on the devices, and then and the partners and vendors are able to incentivize investment into it because they can also unlock more models on their devices, right? So there is a positive feedback loop that is formed here, and that gets us a thriving ecosystem. So you would say, okay, fine, this is all great, cupcakes and unicorns, but how do I do this, right? We talked about all this, but what are the entry points we are talking about? So at a high level, there are mainly two entry points, quantizations and delegation. And these two have, so in the previous talk, Angela and Mangu talked about the export to model authoring to deployment stack, right? The quantization and delegation are the two entry points that are partner specific that happens at different part of this stack. Naturally, you would wonder why these two entry points. So I want to talk a bit about those two. So often enough, when you make specialized hardware for accelerating specific type of compute, their performance and power, maybe they're across different categories. They're optimized for efficient execution across performance, for latency, power, and memory, and things like that. And in order to do efficient execution, you narrow down them to a specific set of data types or things like that. For example, you may have a fused multiply add that is a special instruction or outer product instruction that works specifically for int4 or int8 data type for weights and int16 for activation. Now, in order to take advantage of this efficient execution, we have to make sure that the model generated and trained are actually trained with these constraints in mind. So this is where the quantization API comes in, because you want to be able to specify the hardware-specific constraints in the quantization API. For delegation, once you have the model generated, what you want to do is that you want to have the vendor OEM-specific toolchains, drivers, runtimes, all of that be part of the ecosystem, the executor ecosystem, with a minimal surface of interaction with the system. So the integration points that are provided, the APIs that are provided, are small enough where much of the complexity is hidden and is delegated to the vendor-specific software, which in turn also makes it composable, because your surface is smaller, you just handle what you need to handle, and you give off the rest to the other part of the stack. So in the next half of the talk, my colleague Chen here will walk us through an example model and how we can make use of these two APIs to actually get an acceleration and make execution efficient.
Thanks, Kimish. Hi, everyone. I'm Chen. And yeah, so let's look at one simple example and see how to implement these entry points. This is a common pattern in many neural networks like CNN, etc. So it is an interpolate operator followed by a convolution, and then ReLU, and then softmax at the end. So assuming we have a backend, and this backend supports quantized linear ReLU as one kernel, and it supports floating-point convolution. But it doesn't support interpolate and softmax. So the first entry point will be the quantization entry point. Quantization entry point targets on export IR, and that is the IR right after the torch.export. The recipe for user will be they will call prepare, calibrate, and convert. And then from the last API, they can get a quantized model. The equivalent API also exists for training. For partners, what we need to implement is the quantizer. So the core function we need to implement here is annotate. By annotating the nodes, it allows the backend to convey like what their favorite types of compute they would like to have. Say, for example, if we want to have a 8-bit quantized weight or 4-bit quantized weight, and then this quantizer will be fed to the prepare, and then the prepare is also the first quantization API user will call. Let's go back to the example. Remember, the quantized linear ReLU is one kernel supported by the backend. So in this case, we need to quantize linear and ReLU as a whole. First, we will annotate the input. In this example, both weight and activation will be 8-bit quantized. Then we will annotate the output. We can see from the diagrams, the annotated inputs are the edge to linear, and the annotated output are the edge out of ReLU. In this way, we can quantize linear and ReLU as a whole. Quantization spec is the class we use to describe how we would like to quantize the node. It includes, like, say, D types, symmetric versus asymmetric channel access. It is a rich language to allow the backend to convey like how they would like to quantize the nodes. After prepare and calibrate, after all this quantization API, the last API user will call is convert. After convert, we can get the quantized model. As we can tell from the diagrams, all the things we annotated earlier now becomes dequant and quant nodes. And the dequant and quant nodes contain the quantization parameters like scale and 0 points, etc. There was a poster session yesterday, and there are more details there. We also have detailed documentation available. So yeah, check it out. Yeah, so this is the second entry point for partners, backend delegation. It happens during toEdge, targeting on edge dialect. Before we jump in the delegation entry point, let's take a step back and see what is backend delegation. Backend delegation is a framework to execute PyTorch program in backends outside of the standard PyTorch runtime. Every backend has its own world. It has its own optimization, its own compiler, its own serialization, its own runtime. But we want to make sure the standard runtime is clean and lean. So that's why we have the backend delegation. On a high level, the way it works is user will call to backend API, which will invoke the ahead-of-time components provided by the backend. It will embed a delegated payload as part of the executorch .pte file. And in executorch runtime, this delegated payload will be sent to the backend to invoke the runtime components. When do we need delegation? Well, usually if we want to enable, like, say, part of the program or the whole program on some specific hardware, on a specific backend, to make it either more performant or more power efficient. The backend can either be like a hardware or a software stack. Let's start with the ahead-of-time part. Also, let's go back to the example. After we get a quantized model, remember, the backend supports quantized linear ReLU as one kernel, and also it supports floating-point convolution. The backend will provide a partition function. What it does is to tag the nodes that we want them to run in the backend. And then these tag nodes will be sent to the backend preprocess function and compiled as a delegated payload. This delegated payload will be embedded as part of the executorch PTE file. Also, this delegated payload is an opaque blob. In order to correlate the subgraph back to the original model, the native SDK will also provide enough information for each node such that we can link them back to the Python code. I will mention more details later. Here is our first contract for the delegation entry point. The target IR is Edge dialect, which is core 810 IR, and it has around 180 operators with D types. Edge dialect is really easy to work with. It makes it possible to lower some operators that is not possible to run with the 2010 operator set. After we finish ahead of time, and after we get an xtorch.pt file with the delegated payload, let's see what the runtime part looks like. During runtime, the delegated payload will be sent to the backend init function when loading the method. Remember, this loading part will only happen once. Init is to further initialize the delegated payload, usually for the part that requires information that is only available in runtime. Init will receive the delegated payload and then return an initialized handle. This handle will be sent to the backend during the execute stage. With the handle, the backend can compute the output given the input. And now we finish execution. Let's take a look at the second contract. The backend will generate and interact the delegated payload with the set of standardized API to plug in the backend's own compiler and runtime. The third contract, the delegated payload is fully under control by the backend. xtorch will not interpret it, and it's also the backend's responsibility to manage its resource. At this point, we finish introducing the set of standardized APIs. Are we missing anything? Well, the subgraph now is squashed to an opaque blob. What if something goes wrong? What if it fails? What if it runs really slow? SDK integration is what we need here. Backend usually will provide its own developer tools, and we provide a unified way to plug in the developer tools. The debug handle are integer identifiers attached to the nodes. By compiling the subgraph as one single binary, we sort of lost the graph information. And the debug handle is the bridge to link the compiled delegated blob back to the Python, back to the graph. So say, for example, if something is wrong during execution, like say in this diagram, the convolution fails here. In this example, the debug handle 73 is failing. With this debug handle, we can find out the exact failing node in the graph. And it will point us to the exact line of Python code. By leveraging the debug handle, we can also do profiling inside the delegated payload. As it shows, if the backend supports profiling, and if it provides the profiler developer tools, by leveraging the debug handle, we can enable more detailed profiling inside the delegated payload. APIs we showcase here were instrumental in our engagement with partners. In past few months, we collaborated with industry leaders like Apple, ARM, and Qualcomm, who showcased their hardware acceleration capabilities using delegates successfully. And it doesn't require any change to xtorch core. For users, the flow to use these backends, no matter if it's from Apple, from ARM, or from Qualcomm, the flow is largely the same. We have demos and tutorials in our booth. Please come by and check it out. Thank you, everyone.